Right, hello and welcome to my SIG video where I'm implementing a quad tree for my game engine. I've been looking through several different algorithms and implementing uh, both a R tree, an R star tree, and a sweep and prune algorithm for collision detection on a global level. But I'm not happy with the results. Well, the sweep and prune actually works quite well, and it was a lot easier to implement than the R tree, which took quite a while and was more difficult than I was anticipating. And yeah, and also on top of the problem with just collision detection on a bunch of bodies, you also have updating the position of the bodies as well. And the sweep doesn't really care about that because it just uses the current positions every time. But the R tree, you need to like dynamically update it and optimize based on yeah, if a body travels a long way, you wanna basically reinsert it into the tree or something like that to optimize the tree. And that's quite cumbersome, and it's yeah, it might be more trouble than it's worth, but my implementation is far from like the most efficient solution. It's probably really bad like memory layout, and I haven't really optimized the tanking FPS with just a couple of bodies that are updating their positions. So I try to optimize it the best I can, but I think I'm gonna go with a different route, especially since my game is supposed to be more of kind of a blocky type game with tiles. And I thought that a quad tree would be a really good fit since you divide the game in equal sized squares. And that's kind of perfect for my game because everything is basically a square except for some of the bodies which are rectangles. But I mean, the tile grid and some of the tiles will be, well, I mean, basically the layout of the game is like square based. So what I'm thinking is trying out maybe do a bounded quad tree at first, and then maybe try out to do like an unbounded quad tree. We'll see. I think a bounded would be easier to start with, probably. But yeah, what I'm thinking is that I want a quad tree. I mean, it's going to be 2 dimensions, so it's a 2D quad tree. And what I'm thinking is that for a global collision check, I'm gonna just, so let's say we have a global collision phase. That's when we basically check everybody. Is the collision happening on anything? Uh, well, it's basically, yeah, are there any body colliding with any other body? So what I'm thinking here is like first step is to, well, obviously we need a quad tree and it's gonna be active and all that, and have a bunch of squares. But given that we have a quad tree and the body is inserted into the quad tree, we just do, we go through for each square at the first level. So this is going to be the largest squares. So I'm thinking quad tree is going to be dividing the plane in big squares at first, like the largest type of squares. I'm guessing, well, we're gonna have to define like what the size of the first square size will be. But for each of the largest squares, we are, whoops, we are gonna go through and do a, what I'm thinking is we'll do a broad face sweep and prune here. So sweep and prune for each of the squares, because then, well, you might even you might even combine like each x-axis, like each square that's in the same x-axis. Like if I can pull out GIMP here, we'll see if I can. All right, so we got GIMP going here, and what I'm thinking is that we're gonna have these squares here. Now, let's say that the largest square is basically gonna be like this. So we'll say we're dividing the plane in this size of squares. So this is the largest square, we'll say. It's not perfect because I'm drawing it, but the point is here that I'm gonna draw like an arrow like this. So I'm gonna check like this, and then I'm gonna check like this, and so on. So we're gonna have for each square that basically has bodies in it. Well, or not square, for each of these rows, I guess you can call them, rows of rectangles or squares. Been working too much with arteries. We're gonna sweep and prune each one of those. So what I'm thinking is that this will be faster than sweep and pruning everything at once, because the sweep and prune goes from left to right. Maybe I should go through what sweep and prune is as well. But basically, let's say you have a bunch of bodies in here. So we'll have a body here, we'll have a body here, and we'll have some bodies over here, and so forth. So, and what sweep and prune does is you basically start from the left level, or from the left, and you go like there's like a sweeping line, like this, and it will basically sweep along here, and here you reach with the red line here, you reach a left edge of this rectangle here. So we have a pointer to this. We have basically a sorted list of these edges on the x-axis. So we'll have this here. So we'll encounter this one first. And that means that we add it to our active list. So we have a active list. So active. And we'll just add this body to the active list. Okay, so this is body 1, and this is body 2, and so forth. So the red line now is has added that to the active list. Then it goes here, and so it continues, and then you reach the second box. We add it also to the active list, and now, because we already have one in the active list, so we add this to the active list, and now we have two bodies in here, 1 and 2. And because we have two bodies in the active list at once, that means that they can possibly collide. We can see that they don't collide here, but the computer needs to check this as fast as possible. So what we're doing is we're only checking one axis, basically. We're checking if the left edges comes together. So that means that no one has passed entirely yet. So that means that the x-axis is actually colliding on these two. So they possibly can collide. And the computer needs to check the y-axis as well. And what we do is we fire off each time we encounter a new left axis. We fire off a collision detector, which will check all collisions in the active list, basically for the one that we just encountered. So in this case, we're checking this number 2 against number 1, and if they collide, we add it to the collision pair list. And then we continue going along. So this guy will continue here. And now it reaches, well, kind almost this, but let's say at the same time, but let's say that it reaches number 2 first. What's happened then is it reaches number 2's right edge. What happens then is we just remove this from the list. And that's it. That's everything. That's all that happens, basically. And then this continues. And we reach the end of 1. And basically, yeah, we just remove that. And basically what this means is once you've reached the right edge of a box, it means it can't collide with anything anymore. So yeah, it's out of the list. And yeah, then this just continues here. So now we get a new one. It's get added to the list, but it will disappear from the list right away. So nothing happens with that. That same thing with this one. And all the way this one doesn't, but and here we also get like an x-axis collision because we encounter the first one first, we add it to the list, then we encounter the second one, we add it to the list, and then we have more than one item in the list, and we check the collision against them against each other, and then they get removed. And what happens if you have, let's say we add one more, we add one or like this. Now what happens is that we get over here, we add the bottom one to the active list. So we have this guy, and then we get over here and we add that one to the list. So we got this guy, and then we check this. We can check this guy against this guy because the one we're adding, we're checking out all the others in the active list. They don't collide, so we don't do anything. Well, nothing here is actually colliding, but I'm just showing here so we can understand. And then we get here, and let's say that this left edge is before this right edge up here. They kind of weird here, but in the actual program, these would actually be perfect rectangles. They wouldn't be these wonky blobs. I'm trying to probably should have said that from the beginning. They should be like perfect rectangles. And so we add this to the list, but before, yeah, actually before the algorithm works like this, before you add it to the actual list, you check the collision of the one that you've encountered, so it's this one, against everything else in the active list. So you encounter this guy, you're gonna check him against 1 and 2, and so and then you actually also add it to the list. This time there were no collisions, but yeah, it just keeps going, and then it just removes everything because we encounter the right edges and nothing else. So they get removed, and then we're basically done here because we don't have anything else in here. So that's how the sweep algorithm works, and it's a really easy way to, because it's really easy to implement, it's really fast, it cuts down the collision like the collision checks a lot. It basically goes from checking like, and it goes basically go from O of n squared, because if with a brute force you would have to check every body against every other body, so it reduces the problem of O n squared to, I think it's n times O of log O log of n. So and then with a bit of variation, because depending on how many boxes you have on aligning on the x-axis, because you can have like a whole bunch of boxes aligning here. Then we don't have to check every, even if we're using sweep and prune, we have to check every box in this like basically aligned line against each other, because they all align. Well, not really, but here you can see we're basically having this guy, this 1 2 3 4 5 6 7 8 9 10 11 12. So there's like, you have to do 12 checks against every other 12. So it's gonna be, this inner part is going to be n squared, where n is every other body in here. So what I'm thinking is, by dividing the plane in these basically rows of infinite width and fixed height, we only sweep within one row. So that means that we don't have to check all of these against each other. We only check the ones in this row against each other. So by limiting the height of the rectangle that we're checking in, we could probably eliminate a lot of checks. And yes, we have to run the sweep several times, but we're basically trading an O of n squared again problem against like how, depending on how many rows you have, like row times n, like mn, O of mn, where m is the number of rectangles. So it's gonna be a win either way, unless you have very few bodies, but then it won't take long anyway. So yeah, so that's kind of my idea. Not sure if the idea came through here, but yeah, hopefully it was understandable enough. Let's see. So let's get back to the text code here, and yeah, so yeah, as I was saying, for each, I guess we can say row of largest squares, or row of squares, the first level, the largest squares, we do a sweep and prune on all bodies that belong to to the row. And yeah, and then it's just normal collision detection. So you basically sweep and prune, and you check every body that aligns on the x-axis, or everybody that that overlaps on the x-axis. You check against the other ones, and so then we get our collision detection. Okay, so that's basically the broad collision phase for checking which ones collides against each other. And yeah, and then you can have, because you have a quad tree, and that's one thing the sweep and prune doesn't really help with a lot, is getting let's say, go back here, let's say the quad tree, what it actually helps with is saying, well, it helps with dividing the bodies into these squares. And what you can do is you want to say, okay, I want to throw like a bomb that only damages things within this area. So what you can do is you can say, okay, I want everything. Well, let's use like a rectangular bomb, let's say. So let's say I want everything within this this area. So I want everything within this area to actually be affected by this effect, or whatever you want to do. You want to basically get all bodies that intersects with this rectangle. And if you didn't have a quad tree, you would have to do a brute force method of checking every body that collides with this one, and that's very ineffective. It's an n square problem. If you're using sweep and prune, you actually could optimize it a little bit, because you can say that you still have to check all the way from the left, I believe, because you need to check if any left edges comes here. But once you've reached this point, the left edge of this one, or I should say, yeah, then you're actually recording which ones are colliding. So you basically just ignore any collisions happening before that. But once you come here, anything in the active list will be colliding with this one. And then any other left edges you will have along the way, because you're sweeping let's use this one. So you get over here, you add a bunch of rectangles here, you start to collide with this one. You could wait until the end where you just add which ones are in the active list. And at this point, when you come to this one, you actually don't remove anything from the active list. I guess you could do it like that. And then when you get all the way, so everything also on the way here, you reach a left edge, you add it to the active list. The right edge, you don't remove it. And then when you come all the way over here, so here, now we've reached the end of this. So anything to the right won't collide. So we can just skip the rest. So we can opt, and then you have to check this rectangle against everything that that you had in the active list. So it's going to be a lot of checks anyway, but you skip like a lot of stuff also. But it's not the most efficient from that standpoint. The quad tree is way more efficient of actually finding anything in this rectangle, because what you do is you have this rectangle, you say to the quad tree, hey, I want to find all of the things that are colliding in here. And what happens then is the quad tree is going to say, okay, let's check the largest rectangles first and check if we're going to collide with these I'm saying rectangles, but squares, yeah, squares or rectangles, whatever. And this is going to check, is it colliding with this one? Yes, it is. So let's store this in like a, yeah, let's save this as a thing that you need to check, all the children in here. And then the same for this one and everything else here. So we only need to check all the larger squares. However, there might be some optimization you can do. I think maybe you can even do a sweep for this one as well. And I mean, you can basically say everything to the right of this you don't need to check. And if you have, because these are like evenly spaced and everything, maybe there's like you can sort the rectangles from one axis to the next and have it optimized like that also to skip a bunch of large rectangles, because we really don't need to check anything else besides, like, I mean, yeah, I'm not sure. I need to read up on how the quad tree actually works, because I'm way deep in the OR tree implementation, which is quite different, because yeah, maybe we can I mean, the thing is, why I wanted to have these maybe small kind of rectangle or squares as the largest is because the sweep and prune will be more like efficient, I believe. If we had larger, then we would have to check more things with the sweep and prune against each other. But maybe it's kind of a balance. Do you want the query into the tree to be faster or the sweep and prune to be faster? Not sure. I think it's probably better to have the sweep and prune be faster. But anyway, the quad tree algorithm. So you check every large square that collides with this. So that means you only have to check all these large squares, and you don't have to check everybody against the target rectangle. But then once you have the list of largest rectangles or squares that you are sort of colliding with, then you go ahead and look at each children of those and check. So we only need to check these children. So it's gonna skip all of the other children on the map. And that's way more efficient than brute forcing, of course. And as we've gone through, the sweep and prune helps a little bit with that problem, but not a lot. So it's good to have a quad tree or like a tree type structure that helps you find things in an area. Yeah, so let's see. Let's go back to the text editor and see where we were. So yeah, so the global collision phase, and I'm gonna say like find intersections within rectangle within target. So you can have any kind of shape really. But like a rectangle target or a circle target, let's say if you throw a bomb, you probably want like a circle target instead of a rectangle, and check if you have any intersections with that. And that's going to be way more efficient with the quad tree. So this is just going to be the quad tree algorithm, basically. Intersects algorithm. I'm not gonna explain it in text here, but yeah. So yeah, I'm just gonna start and go ahead and start implementing here. So we're gonna have a quad tree, and it's gonna be a struct, and we might need some generic types. You could have like make this into a function, take a t as the type. That's gonna be like the whatever the entry pointer type or whatever, so to your body object or whatever you want to have in there. But yeah, we're gonna have a quad tree, and it's gonna have some type of node. So we're gonna have a node, and this node is gonna have a pointer to the value. Let's see. So how I did this in the archery implementation, I actually made this into a union of an enum union. And what I did was I had one union which was called the entry, and the entry, well, let's just call this the entry for now. And then so the entry is like the leaf node, or the node that has a child which is like the body, basically, so it doesn't have any children of its own or any other children, so just have one. And then you have the page node, which is a page, and a page is just the collection of nodes underneath it. So I guess for a quad tree you would divide everything by 2 or by 4 or whatever it will be. So you would have like the whole thing, and then you would have like the whole map or the whole screen, and you divide it. I guess you would divide the whole, like you have a size. If you have a bounded quad tree, you have a size of the entire map, and then you start to divide it based on how many bodies. And each, so you would have, first you would only have one page at the root level, I think. And then once you add a couple of bodies and you exceed some sort of maximum, so let's have a maximum entries in page. So let's say that this is going to be, let's say 10 for now. Maybe 10 is too much. I'm not sure. You can fine tune it later, but you have like some sort of maximum, and once you've exceeded that maximum in a page, you do a split. And the split will basically divide the square into 4 squares, 4 smaller squares, I think. And then these 4 smaller squares will divide, will each have the children in them. So and they will basically share the children that was in the parent node, basically. And you keep doing that until you don't have a page with 10 entries anymore. You could imagine if every entry was like in the top left of the square, then it would keep divide until you don't have well, I guess until you don't have that many in, like until you have less than 10 in each page. But I also guess you maybe want to have also like a max height of the quad tree, so you don't divide any more than some sort of threshold. That could all, but that complicates. Let's just start with this, I think. And let's see. So now, okay, so let's see. So we've got our node. We need to have an entry. So the entry should be a struct, and it should have like a pointer to the value, and let's just say, actually, let's actually grab some sort of type in here, because I don't remember exactly how to do like the any type or whatever. It's more it's easier to do it like this. Yeah, and so this will just be a t, and you can choose if you want it to be a pointer or whatever. If you want it to be a pointer, you can pass in a pointer here. If you don't want it to be a pointer, you can just pass in the value without a pointer, but to make it more open like that. And but that you would have to know that it's gonna copy the value basically, and yeah. But let's see. So we got our entry, and let's also do the page. We might need to add more fields to this, but basically this is gonna have a children, and I'm thinking about this because the children is gonna be a list of nodes, but where are these nodes gonna be stored? Now that's a question. I think that you could either, because it's a bit of like a memory, like in Zig, since it's like manually garbage collected and basically memory management is a thing. You have to always think about, well, not always, but you have to think about like where I have a bunch of things, like a dynamic list of things. Where are they stored basically? And if I just do this, like I have a slice of nodes, then, well, first of all, it's a slice to like the actual nodes themselves. They could be copied, or you could store like pointers also, which is probably better because, well, it depends on how you store them. Because let's say you have a list of nodes that is like the global list of nodes, which I guess would be an array list of nodes. Let's import this. So we need an allocator, and we also need, I'm just gonna do this for now. And why is the color weird? Yeah, I'm not sure. Might be because I'm not including this file or something. Oh, I'm missing something obvious, but anyway, yeah, I'm not getting any type information here. But let's okay, yeah, whatever. I'm not gonna deal with that right now. Okay, so it's kind of bad that we don't have LSP right now, but yeah. Anyway, so as I was saying, sorry, the nodes can be in an array list, and so they could be in here, and they could be sorted by which page they are in, right? And that makes it so that the page could actually have a pointer like this, or a slice into this list. And that's a really efficient way of accessing these, because you don't have to copy them over to the page, and the page can modify them basically directly. And you don't have to have an array list in each page, which kind of have to be managed, and you have to you have to have the capacity and everything like that. So you only have one array list. However, the downside of doing like this will be you have to manage this list in a way where it might be costly to have, like, let's say you remove a node. What will happen then? Well, you can't use like swap remove, because then you would put a node, potentially a node that's in another list. There's a high risk of getting a node which is in high risk. You have to do like an ordered remove, or you would have to live with the fact that you have like a hole in your list, but that's not very nice. You could make this like a list of nullables, so you would just set the thing that's removed to null. Also, if you want to insert things into the page, it's gonna be a hassle as well, because then, yeah, you're gonna basically have. But I just thought of something. Maybe we can have like a nullable actually, and you can set the. Let's have like the init function here. You can set the capacity. Let's also have the self. Actually, I don't like the name self. Let's just do Qt for quad tree. So I usually do this so you don't have to like specify the type variables every time. So you do like a alias like that. And let's see. So this is gonna return a quad tree or a Qt, and we're gonna have nodes. So these are gonna be an array list of nodes, node nullables, and we can init the capacity. So, well, we don't know the exact number of nodes that we're gonna have, but we can have like initial capacity, node capacity, and we'll just say that this is gonna be, I guess, for 100 nodes. It's gonna grow probably, but we'll just keep it at 100 for now. And oh yeah, another issue with this I just remembered is if this needs to move to another location, like let's say you increase the capacity and there's not enough memory in that location, and it has to move to another location in the memory to accommodate for all the nodes that it's gonna have, there's gonna be a problem, because every page needs to update basically their slice. It's not really a huge operation, because you can just check each time if the pointer is at the same place, and then you can do each page will you basically iterate, so it's like an n O of n for each page, and you're gonna do like you're just basically creating a slice for each one, and creating a slice is really, really fast operation. So it's not really a huge deal actually, and it only happens if you like insert a node which exceeds the capacity of the current location. So it's probably better to increase this a little bit, so you have like a leeway of that. And but yeah, if you do it like this, and then what I thought was, each page we actually know how many nodes is potentially in each page. It's actually maximum of 10 here. So we have this constant, and what we can do then is say that since each page has a maximum of 10 nodes, then we can initialize the capacity for each page to 10 children. And so when you, let's say, want to insert a new node into the page, it says, oh, either you've exceeded 10 and then you have to split, so it won't get into the page anyway, or you actually know that you have enough capacity in the page, so you can add the child to the page. So you don't have to worry about, well, you still couldn't do a swap remove, but a remove would actually, instead of swap remove, you would actually just do you could do like a special type of swap remove, like a swap remove, but inside of the page itself. Like we can actually, if we go to the, well, I don't have my LSP, so I can't go to the code here, but oh, there was an error here somewhere. Oh, this is, so the LSP does, no, it's not the LSP, it's like the, I don't know, it's like a built-in, there's like I have LSP, and then there's like, I don't know where it comes from, but it's like a check that NVim is doing with Zig, and it's automatically putting things in the quick fix list, and yeah, it's really bad. I'm not sure how to disable it, but I want to disable it because it's annoying. Anyway, so yeah, we could copy the swap remove function and then modify it a little bit to make it work for each page. So each page would be what we also could do, because there's another thing called a buffer list, I think, which is basically a list that has a static length, and it keeps track of like how many items are added and stuff. Maybe you could do something with that. Yeah, anyway, what we really just need is some way to append into a page, some way to remove, and the access. And the access is easy because you just do a slice, and if you have an evenly spaced out list of nodes, like you have 10, the first 10 nodes is going to be for the first page, the second is going to be for the second page, and so on. So you could actually divide the pages into, like, the pages have indices, and then you can just calculate which slice of children you would have. And all this will be to avoid having array lists in each page, because for one thing, the nodes will like end up in different memory locations, and that's not good. And also, yeah, there's a little bit of cost of managing each array list as well. Each time you append stuff and remove stuff, there's like a bunch of checks going on. We can basically avoid all that if you use this type of structure. Okay, well, enough about that, but that's like the memory management and optimization you need to think about when you're using Zig. And it enables you, is like a lot of potential. You can basically do whatever you want, but you really have to go and think about how you're storing this. And you can choose like just the simplest to start with, which I actually encourage when you're doing something new. Start with the easy stuff and then get it working, and then think about how you can optimize it. But since I've already implemented an R tree, I already did that way. I already did like having pages have array lists and stuff, and it was a pain to actually do that as well. I mean, sometimes the more simple way is actually easier, faster, and the best way to do it. This might be the simplest way of doing it. I'm not sure, but yeah, it's just an idea that I have. So anyway, yeah, so the page needs to have children, and what I also like to do is have the bounding rectangle, which I am calling the AABB, like axis aligned boundary box or whatever it's called. And I already have a structure for that, so I'm gonna import that. And it's going to be import from physics shape.sig. There we go. All right, we're back, and yeah, the LSP is working here. Great. Now, I'm curious because I think there's something called like a buffer list or something, ring buffer. Interesting. So array, a bounded array. Yeah, so there's like something called a bounded array. Bounded array. And this array, so yeah, yeah, this is a bounded array, so it's gonna be like a static array. Yeah, that's not really what we want, but we want like an array type struct that we can like hash map. No, it's not a hash map. So we have an enum array, multi-array list. Not sure what that is. Multi-array. Stores a list of struct or tag union type. Instead of storing a single list of items, store separate lists for each field. Oh, whoa, 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 whoa. Okay. So this will maybe help with like vectorizing operations. Multi-array list. That's really, and this is the really cool part about SIG, that you can actually have this kind of structure, which you can actually define yourself. You have like user code or user defined stuff that you can actually implement this type of structure, which is really like in other programming languages, you would have this as a built-in functionality or feature of the language. But in Zig, you can actually extend the compiler with this type of functionality, which is really cool. So what I think this does is you have a struct, let's say just a simple example. So you would have a vector with X and Y floats, like float 32s, like two float 32s, one for X and one for Y. And then what the multi-array list will do is we'll take each field, like the X field, and make it into an array. So we would have it's the thing called like the structure of arrays instead of array of structures. And that helps with, I'm actually using that right now with a custom structure that I'm using for vectorizing, updating positions in the physics engine. But this actually automates the construction of those types of things. So that's really cool, actually. Huh. I wonder how it works with accessing and doing stuff with the actual fields. This allows for memory savings if the structure union has padding, and also improves cache usage if only some fields or just tags are needed for computation. Okay. Right. The primary API for accessing fields is the slice function, right, which computes the start pointers for the array of each field. From the slice, you can call items field name to obtain a slice of field values. For unions, you can call items name. Okay, that's really cool. I want to play with that sometime, but now I have something else I want us to do. Okay, so can't really find a good, so we might like end up implementing the type of array that we need for this, which is basically what I want. Is just like you have all the array functionality, like you have append, remove, and all of that, but you use an already existing slice. So you would initialize it with a slice, and then you can also do like, yeah, I wanna like set the slice myself to something else. So now I wanna make it point. So I wanna set the slice myself. I wanna set the pointer to be somewhere else, and then it's just gonna operate like an array with that slice. So you would have the length, you would have the items in it, and you can operate on the items. You can do append, you can do swap and all, swap, remove, and all that. That would be really cool, and sort as well. So yeah, I think we're gonna need to do that. For now, I'm just using a slice here, and I'm gonna think about more how this will work. All right, so yeah, that's gonna be it for today, and yeah, I'm gonna continue with this and think about how this will work, and I'm also gonna read up a bit on how the quad tree algorithm works, so that we'll have a better understanding on how it actually works compared to an R tree, which works a little bit different. So they're quite similar, but there's also a lot of differences. But yeah, I'm gonna read up on that, and yeah, see you next time. Bye.